We can do more with modern technology and less humans than what anyone could have imagined in the 80s. We can communicate quicker and more effectively. We can bring the right information to the right people at the right time. In the early days of the boilers, every piece of pipe or tubing or every connection was somebody's interpretation of physics. The American Society of Mechanical Engineers built this code, and what it does is it creates predictability in a highly unpredictable area, which is human beings. The databases and the interfaces between the databases are excellent. The tool to communicate these things is limited. There are times when the tail wags the dog and we make decisions that cost us money to make sure that our computer tools are working properly.
I am Rakesh Agarwal, the CEO of Piping Technology and Products. And as we approach our 50-year anniversary at the company, we're starting a series where we interview some of our favorite customers. And today I have with me John Schmidt, who is the Global Expertise Area Leader for Dow Corporation. So, John, thank you for joining me.
Thank you for the invitation. This is an honor.
Yeah, it's great to have you here. You've been a friend of Piping Technology for many years. As I canvassed the team and asked, hey, who should I interview in this first interview for Piping Technology, your name came up, I think 3 out of 3 for the people that I talked to. So,
wow, well, thank you.
Yeah, so I'm honored that you're here to join me. And as we've gotten to know each other, you have a really cool and diverse background. So I'm excited about not just talking about your, strictly professional interests, but your broader hobbies as well. Why don't we start with your telling me a little bit more about what you do at Dow? You're the Global Expertise Area Leader for piping, and so we work together a lot, Piping Technology and you on projects. But just more broadly, what does your job entail at Dow?
In general, I interpret code, whether it's ASME B313 or 311 or 314, into policy decisions and actual designs. So a lot of my days, I'm giving advice to young engineers or designers who are trying to create a design for a chemical plant or a pipeline that will keep them safe and keep our community safe, and interpret the code in a way that will lead to a predictable and reliable operation. So while I'm definitely interested in keeping costs low, a lot of those costs that people overlook are long-term costs. So I write procedures, I read code, and I advise the next generation.
So for people who might be listening and not familiar with the codes, could you describe briefly what these codes are? What are these ASME codes?
Well, a lot of the power of our modern piping system comes in our standardization. And in the early days of the boilers, and some of the early boilers you can see in museums are completely non-standard. Every piece of pipe or tubing or every connection was somebody's interpretation of physics. And so the American Society of Mechanical Engineers, and the idea of keeping safer and more reliable operations, built this code. So 313 is process piping. So it's pipes and pipe components, or really it's just pipes, not components, inside the battery limits of a plant. And then there's several other codes that describe, a flange needs to be standardized in this shape or in this material or this testing. And what it does is it creates predictability in a highly unpredictable area, which is human beings. Right, so turning math into human activity in industry is it's a difficult thing, right? Mm-hmm. We have our language and our codes, and now whether you're in China or in Turkey, you can take an ASME 16.5 flange and know predictably what it will do. So on the sharp end of the engineering stick for our chemical process industry, we have people that have a lot of competing requirements, right? We need to keep it cheap. We need to keep this supplier happy. We need to keep this, vendor on our side. We need to keep this client. It's too much to think about. So the more we can compartmentalize that, the less decision making that we have, the decisions become better. So the codes help reduce those things at the design level.
One thing that we talked about was this idea of academic knowledge versus pragmatic knowledge. They're the knowledge that is informed by hands-on experience versus not. So talk a little bit about that.
Well,
feel free to use the word knuckleheads also in your.
Knuckleheads. No, I had an experience at the shipyard where I was asked to heat treat a bunch of steel coming out of China. So some fabricated legs for a platform rig, oil rig.
Yeah.
And my response was to go online and find somebody that would sell us a big expensive furnace. And the engineering manager got a cargo box and put barbecue burners in it and temperature sensors and built a heat treatment center for less than 1/100th of what it would have cost to purchase a heat treating furnace. That's something they don't really teach, right? That's sort of the initiative, and he did successfully heat treat the entire set of steel, saved hundreds of thousands of dollars, right? Not only in capital costs but also in schedule. That sort of thinking is not going. I don't know if that's coming out of our universities, right?
Yeah.
I had more than one student here in America, and one student here in America and two in Europe, who was not comfortable with the precision of the code. And they said, well, they didn't want to take the edge cases. They were afraid with the risk from inspection that didn't inspect every single point. Because they were afraid of unknowns. Yeah. And we can't operate in a world without unknowns. I like to reference, even though I don't totally understand Gödel's proof, I believe, and correct me if I'm wrong, if the gist is that any sufficiently useful mathematical system will have unknowns or contradictions. And there's something true about that in our engineering, right? That we have to take some risks. I think a lot of people choose engineering because it is less risky, right? I chose engineering because it was less risky than being a lawyer. I was considering being a lawyer when I was younger.
Yeah, people like problems that have a closed form solution.
Absolutely.
Right, or a bounded set of solutions.
Pure mathematics, even with units, can have perfect answers that are not left to interpretation. That's not the same thing in engineering. So that pragmatic understanding of risk, precision, those are really important topics.
Yeah, just the inclusion of risk as a factor, changes the way you look at an engineering problem. And,
right.
That comes from more from experience than from book learning.
Right. Well, and we understand as engineers, even fresh out of school, and a lot of people understand this before they go into school, that we have a duty to the people around us to keep them safe, to our communities, right? It's not, our transactions with the world are not just a paycheck and a set of designs, but as a professional engineer in the state of Texas, I have a obligation, not just a moral, but I believe a spiritual obligation, to protect the people around me, right? And so doing that while at the same time understanding that there are things out of my control, there are things in this design that are not 100% perfectly, analyzed after the mill. The steel isn't analyzed every single piece after the mill. Not every stick welded connection is radiographed, and we have a lot of ways to protect against those things. But there is some imagined things, right? That's hard to teach.
One thing that we talked about was how this aspect of hands-on experience is generationally different. That if you go back 50 years ago, the engineers that were coming out of training grew up in rural settings, perhaps, where the life required hands-on. Tell me more about that. And even you also shared how that is reflected in the academic textbooks of that time versus today. So
I believe that engineering used to be more of a hands-on educational experience. People would, shade tree mechanic was a thing in the 40s and 50s. The idea that people would go fix their own cars because they were simple enough to understand the levers and pumps involved in their own cars. And so having your hands on a piece of equipment and understanding how it moves, or tearing it apart, breaking it apart, or putting it back together, I think having some of that experience in your life before you go into an academic environment can lead to a great appreciation for it. So at Lamar University, I had the pleasure of a very well-developed laboratory. We ran water treatment plant for 6 weeks. We ran a distillation column for a few weeks. We ran actual process chemistry where it was there in front of you. You could put your hands on it. And that led to an appreciation for what the numbers really meant. And I don't know how that is in every environment, but I think that that's something every engineer should do. So one of the things that I've decided to do in my free time is to have a lot of crafting hobbies and hobbies that will give me a better feel for how to work with my hands a little bit more. And that has had, I think, spin-off effects on my professional life.
I want to go back to engineering education. This is something that we talked about. This and you mentioned, right, at Lamar, you had this experience of running, did you say a water treatment plant?
A very small, like laboratory scale plant, yeah, or pilot. I would call it pilot scale.
Yeah, great practical experience.
Absolutely.
What's your view of, and be opinionated, please, but what's your view of engineering education today? And what's missing?
Well, to cushion this, I haven't been in a classroom for engineering in quite a while.
Yeah.
From my perspective as somebody in industry who prepares fresh graduates, I would say I want their hands on things. I really need a more pragmatic approach, people more interested in actually doing things, right? Because I feel, and it's a difficult needle to thread, right? Because we sometimes we don't get to do anything. We make a design and the building never gets built, or we build a chemical plant in 3D and bytes and bits and we never see it. But I would like to see more pragmatic, hands-on experience. So chemical engineers that have seen a pump and can see, what it means to have, head rise, and mechanical engineers that understand what turbulence sounds like, or cavitation sounds like in a pump. Like these are, it's the education that you can get in laboratory scale can save us on the industrial scale, and that goes a long way.
Yeah. In your professional life, is there, through partnerships, are there ways in which you're, creating this reality with, with graduates or, students that are with students?
I've had a few interns, and the thing is, in my area in central engineering, interns aren't getting the best experience that they could.
Yeah.
Now, my company does hire interns and sends them out to the field and gives them dirt under the fingernails, as I like to call it.
Yeah.
And I cannot stress enough to the young engineers in the world that this is the pathway to being an engineer. Whether it's, and these, co-ops are paid, so they're treated well. And they definitely have to work. They need to understand professional etiquette before they get to the field, or that could be a problem. But that's really where you find, a 25, 26, 30-year-old mentor, and you start to really learn how to do things.
If there's a fresh graduate or soon-to-be graduate that's listening to this, what's a path for them to get that dirt under the fingernails experience? You mentioned working in a shipyard, and you actually put your studies on hold to go and take that job, and you gained a lot of practical experience from that. It sounds like you connected with people who then led you to your next job. What's a place where there might be an alignment of that practical experience and also a need for young graduates?
First and foremost, there are programs at most major universities that help interns find placement. That would be the most conventional route, and I would recommend that. And some unconventional routes are to get jobs adjacent to the job that you want, and to learn from those. And that's so. When I went in as a piping designer at Beacon Maritime, I was not an engineer, and I was not getting paid as an engineer. And I chose to do engineering at night and on the weekends in non-conventional ways, and not being afraid to do things outside of your pay, right? And I know nobody wants to do work for free, and there's a lot of people, okay, I don't need to do that. But that was a great bit of training. I think there was some things, what was it called? Overemployed? No, overemployed is where you have too many jobs. There's something quiet quitting. There's an opposite of quiet quitting called quiet hiring. Somebody was making up some word about it.
Yeah,
Well,
you do something for free.
Right. So I've never been afraid to do that. Right.
Sure.
I want to learn the way to do it. And usually when you're learning something in an adjacent field, it helps you do your own job, right? Whether at Dow Chemical, we do something called a temporary assignment, and it's or temporary developmental assignment, and it's specifically there where where a person will work in an adjacent role, and they'll learn some of the edge cases, like why is it important to have this quality number go in.
Right.
That's useful.
Yeah, look for opportunities to cross-train.
It's quiet hiring, cross-training opportunities, internships. Those are, sometimes that's what you have to do. I'm not suggesting anybody go work for exposure only, but unfortunately, sometimes that's the way it works out.
Yeah, and I like the suggestion about looking for opportunities in an adjacent field. Like that's I think a great idea. Like for example, your goal might be to work at a large chemicals company, but then you can work at a manufacturer. I think, for example, our environment at Piping Technology offers a lot of really pragmatic, hands-on experience, and a lot of opportunity for that kind of learning.
Absolutely.
Yeah.
My sister worked very hard to get into the medical field, and she couldn't find a way into it. She hated college. But she got a job. She joined the military at 17, as soon as she could, and got a job she tried to go into flight medic, and they had her be a secretary. And she worked, and she specifically made friends that were in the field and quietly hired herself in some of their less pleasant tasks, and then got hired at a doctor here in Galveston as a secretary, and did extra work on the weekends, and eventually was able to get transferred through the military into the flight medic program, and now she's a senior chief in the Houston Fire Department doing medical work. So, So she was a good example of that, and I learned from her.
Yeah, which just kind of kept being useful and used that to shape her career.
Absolutely. Absolutely.
So going back to engineering education, do you guys have partnerships? You mentioned industry partnerships, that could be something that fills this experience gap for academic engineering programs. What does that look like at Dow and other places? Aspirationally, what does it look like?
Aspirationally, what I would like to see?
Yes.
I would like to see more collaboration with research projects with teachers, with educators. Right now, I'm working on clarifying the buried pipe guidance in ASME 31.3. There's a lot of contentious debate about how we should design underground pipes. Yet our society has been building underground pipes since Mesopotamia, right? So you figure there wouldn't be a lot of argument about how that's done, but there is a lot of argument. It's a multi-million-dollar question today. I would love to partner with a mechanical engineering professor and set up experiments and reconsider some of the equations that we use today, some that are maybe applied poorly or change the wording in some of them. But it would be nice to have a partner in that research.
Yeah.
We do take on our interns, but it's not the same thing.
Sure. Let's talk about technology a little bit. You know that I have a background in technology as well, in addition to piping technology. Information technology, software, and so you've been in the industry for a long time. What's the role that technology plays today, and how has that changed the way the business works?
We can do more with modern technology and less humans than what anyone could have imagined in the 80s. Right? It takes less people to do an equation, to do a design. We can communicate. We can communicate quicker and more effectively. We can bring the right information to the right people at the right time. So we can automate a lot of the things that are boring. When I first started this business, I had to draw pieces of pipe, each line manually in AutoCAD. And now we have tools like S3D or Caesar that can automate the process of doing the drawing or doing the calculations.
Right.
So in the days of my grandfather, static analysis for structures or pipes was done by manually performing matrix. And now Caesar does that for us with a great graphical interface. So while right now I'm talking about advances of a generation or 2 generations ago, we see more interesting developments come up. So our front-end loading analysis can turn a block diagram, so a non-geometric idea of a process, into a geometric idea of a process that can be more quickly communicated to the engineers who can validate it. The technology of a pipe has been around for 2,000 years, more probably. But the way we interact with those, that's rapidly changing. Technology has changed in the code in the last 5 years dramatically with, like I said, the 31J advancement. The computers are changing the way we communicate that internally. There's a lot we can do.
Yeah. So part of what I heard you say is that the tools, we went from, having primitive CAD tools, where you could draw things instead of on paper electronically, to these verticalized tools that were specific for plants and for piping, and then engineering tools that further layered on top of that, like Caesar, that will do the stress analysis. Just so that people who may not be familiar with the tools understand them. Could you walk through you mentioned S3D, Caesar, what purpose they serve in the life cycle of the design of a plant?
So a chemical plant will start off as what's called a block diagram, which will be on a piece of paper or on a screen. It'll be a square and it'll say distillation column or reactor. And the pipes and processes won't be shown geometrically. It'll just be shown as a single line. Now that's the early stages. And a chemical engineer...
Right, I was going to say that comes from the chemical engineer.
That'll come from a very senior chemical engineer and a business guy.
Okay.
So a project manager, so a money guy. And then the chemical engineering team will then put together a P&ID. So a P&ID is still relativistic, a non-geometric diagram of how the chemicals will flow, right? So the fluids will flow, whether they're solids or liquids. And some companies include the control logic in that. I think we don't at Dow. But and then from the P&ID, that'll go to a front-end loading team. The front-end loading team will be designers, a mix of designers and engineers, they'll create like a geometric model, and that will be in I think there's another interesting piece of software that actually will turn the P&ID into the early geometric model, and then that can get exported to S3D. S3D it's a database that includes elements about geometric shape. So it doesn't do any engineering, but it becomes a way for a designer to put things in space, and things will take up space, and they'll have mass, and they'll have other properties, right? So those properties, we take these bits and boops of information, and once it turns into a geometry that can be represented on a picture, that starts bringing things, more realistically to the human eye, right? So then at that point, we'll bring in people with experience running a chemical plant. They'll say, okay, well, this needs to move over here or over there. That information could get downloaded directly into the engineering tools, which the translation, each step along the way of the translation is a challenge, right? So,
right.
And actually, I could go on volumes about that challenge, but yeah, the easier to have the different databases that hold the information, the easier it is to transfer them between the different analysis tools. We need less and less people. We need smarter people. We can do more with less. We're more efficient. We're more responsive.
Yeah.
So
Timelines get compressed.
And a lot of, in my early days of the career, I didn't understand why that timeline was so important. During a project, the money is sitting somewhere, not being used, right? The promises the promises of that dollar bill in the bank account aren't being met. We need to put that money to work. We need to make jobs. We need to make products.
Could you give an example of the timelines getting compressed? Like how long would certain things take from that block diagram to the P&ID to a physical representation of the plant and the engineering calculations, before versus now with this, integrated workflow that's data-based and, tied together.
There's a lot of variables in that. No two
course.
chemical plants are the same.
Exactly. It all depends,
No two
right.
teams are the same because, of course, in my scope, I have both the Dow Chemical Company and some of our business partners like Fluor, Worley Parsons,
Got it.
formerly Mustang. I would say just in my life, which is a little less than 25 years, a little less than a generation, I would say we've shaved 40% off of the cycle time.
It takes nearly half the time to do something versus before.
Yes. With the same technical expertise and organization, because the technical expertise are still incredibly important. So as the tools get more complex,
The judgment that we
the
talked.
judgment gets more, absolutely.
Yeah.
And
Yeah.
so communication, training, experience, right? These get really important.
Yeah. Yeah. Well, garbage in, garbage out, right?
Absolutely.
Yeah.
Well, and not just that. Well, the software tools and the database, the databases and the interfaces between the databases are excellent, but the humans might be used with or have a experience with one system that may treat one bit of information differently than another, right? So what might be a Boolean or a simple number in one system might be a number with precision in another system, or a range.
Sure.
And that may sound unnecessarily technical, but it's important.
Yeah. Yeah, definitely, because you're feeding the data between the systems, and that's probably where the problems occur.
I have an example. It's kind of funny.
All right.
But I'm doing work with a design group, and there was a piping lead at the meeting. The project had totally gone off the rails, was over millions of dollars over budget. And this particular group was doing the detailed design, so the geometric side. They were taking the P&ID and making a geometric model.
Yep.
A different group with a different organization, different company entirely, had done the engineering. And at one point in the engineering, one of the things they have to do is they have to tell me the temperature that's going to be in the pipe, the temperature of the fluid in the pipe. The detailed design lead was saying, well, I'd questioned the design temperature of the pipe. He said, well, the design temperature is the design temperature. And that sounds great if you're a programmer and you have a variable called design temperature. But in the pragmatic real world, the design temperature is not the design temperature. And this was a hard lesson for me to learn, because the design temperature from a chemical engineering perspective is, it can be, well, what if three things go bad all at the same time and something terrible? Once every 2,000 years, we could reach 400 degrees Fahrenheit. But in reality, from the mechanical engineer, from the piping side, my design temperature is something that's going to happen every day and not happen every day for 20 years. And that's a different story, right? Fatigue life is something different. So the design temperature is not always the design temperature. And in fact, the process engineer clearly had no pragmatic idea of how to build a chemical plant, or was so afraid of some strange thing happening, a meteorite hitting, that he told us to design a chemical plant that would have to survive. And it was literally more energy than a nuclear blast. I said, okay, we have to reconsider
400
what
degrees or
right.
Yeah,
And if you're thinking zero risk, if you're thinking in a programmer database, that's not the same thing.
Right.
Because in their database, in their network, design temperature is design temperature. And in reality, the mechanical side, I want something that can survive 7,000 cycles.
Yeah. What are the downsides to technology being such a central part of the process? Time schedules are compressed. You can be more responsive to customers, be more efficient, get more done with less.
In one aspect of my role, I am creating pipe specifications for every chemical plant at the Dow Company, for everything, for FRP, for steel pipe, and for whether it's an electronics plant in Korea or whether it's a well-known refinery in Texas. The tool to communicate these things is limited, right? We have technical limitations on the mechanical engineering side. We have technical limitations on the technical tool, on the software side. There are times when the tail wags the dog and we make decisions that cost us money to make sure that our computer tools are matching them, that our computer tools are working properly, even though we don't need this expense in our mechanical engineering lives. And there are some risks that how we communicate those things within the limitations of the tool will be misunderstood, maybe not by our culture, but by different cultures.
Yeah, by the way, I've been using the self-driving feature on the Tesla only for the last 2 or 3 years. They made it a subscription. I was unwilling to pay whatever $10,000 to get it, forever. But when they started charging $100 a month, I was like, yeah, I'll do that. And I've realized it's not that it's a new kind of driving.
It is.
Right? It's there's sort of a lower awareness and focus that you can have on driving, but it's not no focus.
There's an interesting book, and I can't remember the name of it, sitting on my bookshelf. It's talking about engineering through the ages, and it used to be that cloth was woven by hand, and when the spinning wheel, I think it was a spinning wheel, came around, it was a lot more mechanically assisted. There was there was actually written stories about people said it was terrible because this new, equipment assisted cloth was too coarse and unpleasant and not helpful. And I wouldn't possibly think of going home and weaving some fibers together for the next shirt I'm going to make. So,
yeah.
Things are changing.
It's inevitable. The advance of the technology is certainly inevitable.
Well, it's a truism that we're afraid of change. And there's reason to be afraid of change. The existing system is known. There's so many unintended consequences of changing things, right? That in any change, especially when we're talking about, our companies and our families and our safety, any change should be carefully scrutinized. There should be a reason for change. And so people are naturally afraid of change because of the unknown. But there's a place for it. And I think you've nailed a lot of great topics on it.
I just became CEO of Piping Technology 10 months ago.
Congratulations.
Yeah, thank you.
It's a great group.
I love working in the company. It's a really wonderful culture, and I've been a part of it since I was a kid. I grew up in the business, and so it's been a lot of fun for me to come back to the company. Now I come from having spent also a lot of time in the software industry, and here's a question I want to ask you. On the topic of change, do you think that let's just broadly call it the industrial space, that we are more change averse than, say, other industries are, and that we could be more, embracing of change?
I think
Are we slower to change?
There are systemic reasons why we're slower to change. We're still on the imperial system of measurement because we're tooled. So we have tools, we have existing infrastructure that, like I said, it's not sexy to go change out all your wrenches, right? So we have infrastructure already, and we have risk. We have greater risk. We have lower tolerance of risk. There's, like I said, I'm okay with risk in social environment, but when we're talking about gallons of carcinogenic fluids, I'm not going to take a risk easily.
Yeah.
So I think it's good. We need to be that. The HBO did a great series on Chernobyl, and they did a great job describing how the thinking, like party thinking without pragmatic feedback, could lead to terrible stuff. So I think it's related to that.
Yeah. So it's matched to the what's at risk.
Absolutely.
Yeah. So Piping Technology, you've been a partner of ours on over many years. I would love to hear if you have any stories of where Piping Technology has been a good partner to you.
Well, I mean, I definitely have several. I have some really boring ones. I can say that in the entire time that I've been at Dow, I have predictable, reliable, good cost piping supports, piping shoes, understandable technical guidance. So Piping Technology is a name I could trust, right? While any individual component of a chemical plant is cheap, of an industrial facility might be tiny, the impact of losing it can be significant. Everything has to work, and everything works. From Piping Technology, I get chemical plants that get built when we expect them to get built and that work. I got to say, I have really loved working with your U.S. Bellows subsidiary. which is I've loved watching them develop. Their ability and their responsiveness has been great. At one point, I had a facility in Texas City fail, and part of the reason it failed is somebody had designed a strange piece of pipe that really didn't fit, but we could fix it with a custom support. I needed, part of it had to slide, part of it had to be fairly precision. And I had called Mr. David Baker and I said, listen, I've got a weird one for you, and it's Friday at 6 p.m. And he said, well, send me a drawing. We can. I said, no, I need this plant up right now. It's quite a bit of money, and your team did it, right? I was able to show up on site with a drawing. I got to watch them make it. And we got a really custom part quick. So,
yeah, I think we're actually more piping technology than any other moment in moments like that, where somebody has, like what you said, which is like, we have this weird problem. That's when the organization sits up and says, all right, this is our moment.
Right. And somehow you're able to do both. And I can appreciate that, because there are times when I want it off the shelf. I need some predictable thing that you built 3 months ago that you've been building for a generation, and that I was able to plan last year to have this here at this time, right? And predictable, right? That there's I don't like surprises, and I definitely don't like surprises when I'm spending somebody else's money, and I consistently get a reliable partner with PTMP.
Yeah, I'm really glad you mentioned U.S. Bellows. U.S. Bellows is this rocket ship within the company that's been growing year after year. I was involved myself in a lot of the acquisitions that led to, all the different, we acquired several expansion joint manufacturers that, have made U.S. Bellows what it is today. But yeah, it's a growing piece of our business. So it's great that you've worked with them. Thank you so much. This has been a lot of fun, and you're a fascinating person, and I think our audience is going to love hearing from all of your experience.
Thank you for the opportunity to be here.
Yeah, awesome.